Okay, I think Hagar the Horrible is still in the news, right? And I guess one way to stop an army in Hagar's time was rust. And the point being, rust is it's an electrochemical process, it's an electrochemical reaction with iron and water and oxygen. And it's just one application of electrochemistry and how, if you understand the chemistry of it, you can actually stop rust from occurring. And they use what they call sacrificial anodes, something that will react before the iron does. You can't really stop the electrochemistry. It's going to happen, and it's going to be a lot cheaper than iron. And we'll talk about the exact metal and how this really works probably the next class period. But the point is that it works. And you can see how it doesn't really matter where you put the little hunk of metal, the sacrificial anode, like here, it's right there. And you just have to have an electrical contact with the iron. And look, here's another one underwater protecting somebody's dock or something. You have them in sidewalks and streets and things. Okay. One thing I think that's going to be confusing about today is all these words are the same thing. They say cell potential, cell voltage, electromotive force, EMF, E-cell. It's all the same thing. If they say standard cell potential, standard cell voltage, standard electromotive force, standard EMF, standard E-cell, all the same thing. Okay? And what is pretty much all this stuff? If I and have Matt hold it here, if you look closely, it's the D cell. It has 1.5 volts. Turn the little machine on, put the red to the plus, black to the minus side, and it reads 1.598 volts. So Energizer, they bumped it up a little bit, right? It's supposed to be 1.5. They bumped it up because then the thing will last longer, right? Kind of crappy thing to do, don't you think? Anyway, what is this thing called that I measured 1.5 volts on? Voltmeter, right? We've been drawing a circle, putting a little V in it, right? There's our voltmeter. So that's what all this stuff is. It's what you measure on the voltmeter, okay? And to me, it's a lot easier just to realize all these terms, cell potential through E-cell, they're all some number of volts, right? That's really what all that is. It's what you measure on the voltmeter. Okay. Let's take a look at maximum electrical work. So with this term, you can answer questions like what's in green here. 45 grams of silver is produced for a voltaic cell with EMF 1.15 volts. Then they give us their reaction. Well, to put this in perspective, Energizer, I'm sure, doesn't have their little reactions inside the battery involving silver. It'd be way too expensive, right? But it could just as well, you could silver and magnesium, right? There's the reaction going on inside, and you have to separate the two cells somehow and make it all nice and compact, and it ends up looking like a battery. And the voltage is 1.15 volts. So you take this little battery that has that reaction going on inside it, and you put it in a little car, right? Little car goes a certain distance, in other words, a certain force occurring over a certain distance. What just happened? Work. The little battery actually lost energy or gained energy? Lost. Look at that. That's where the minus sign's coming from. Losing energy. Okay? And so it's not really negative energy. They're just trying to keep track of energy, where it's going. What are the units for work? You remember? It was joules, because work is energy. Energy is work. Work is just in different forms, transforming energy from one form to another. That's really what work is. But that's more for more advanced classes. But anyway, so you see this question, homework, use this equation, and then right off the bat, you're supposed to know what S is. You're supposed to know what E-cell is. Now, I don't know if you picked one of these up. I wrote a little sign that said, please take one. Did you guys grab one? No? Okay. Oh, I think you have an extra one, though. 1, 2, 3, 4. Okay, now these are the exam 4 equation sheets. So let's see if you have one. Okay. And let's see if Javier can find what F is. It's on the exam 4 equation sheet. This is your copy. See, it's up there with all the constants. What does 1F represent? Yeah, do you see what the 1F is? 1F equals what? Anybody see it? Victoria, do you see it on there? 96,000 C over mole E minus. Okay, who's had general physics? Anybody? Jasmine's laughing. She must have had it. Juan, no? Juan had it, right? Okay. C, that's a unit of what? Coulombs. It's a unit of charge. Grams or kilograms. Well, you have units of charge, coulombs. Okay? So there's 96,485 coulombs in what? Mole, MOL? Probably. Mole of electrons. Take a mole of electrons and there's 96,485 coulombs of charge. Okay. So you're supposed to know that right off the bat. And then, Jessica Rojas, you're supposed to know E cell. It's the volt. Right? It's confusing. It's confusing. Right? All of these mean the same thing. They all mean the volt. Even if you put the word standard in front of all those, it still means the volt. So it's just the 1.15 volts. It's right there. Okay. Okay. So I think the real work, Mallory, is getting the little n. Where's Mallory? There she is. It's getting the little n. And there's a hint. Hint. N is the number of moles of what involved during a reaction? Electrons is right, but you could really pick something else, but then you couldn't use F. What I mean is, they said 45 grams of silver. So you could use the moles of silver to figure out the max amount of work. But if you use moles of silver, you can't use the F, because F is in moles of electrons. So the best answer is electrons. Technically, you could use anything. The answer is electrons. So you get N by its number of moles of electrons, and you find it using an appropriate half reaction. Okay. We'll see if we can figure out what that half reaction is. Let's go ahead and let's solve the question. So we're supposed to say, all right, let's find W max. W max is minus N F E cell. So minus N. F is my 96,485 coulombs per mole of electrons. My F, we said, is 1.15 volts. Whoa. All I got to do is find that little n. Okay. So to find the little n, we're going to use an appropriate half reaction. I mean, this whole mole bridge idea. We're going to convert the silver that reacted, or didn't react, it was produced. How do we know it was produced? Because the silver solid is it's a product or a reactant. It's a product, right? There's silver. That's why they said produced in their reaction. So we're going to convert. They could have told us any of them. It doesn't really matter. but they told us the amount of product produced. So we're going to convert the amount of product produced into electrons. We need a reaction. So we can do the whole mole bridge idea. So it pretty much start out looking like this. We're going to have 45 grams of silver, and we're going to convert it all the way to moles of electrons. So we need an appropriate half reaction. Sylvia, have an idea what that appropriate half reaction might be? Now there's two routes you can go to answer this question. One is to use the sheet, okay, and find a reaction that has, right? We want a mole bridge with silver solid and electrons. We want to know how they're related. So you see if you can find a half reaction with silver solid and electrons in there. Do you see one? You see one in there? Anybody see one? Okay, so what's the whole? How does the whole reaction read? Ag plus 1 electron equals Ag solid. That's one way to get the appropriate or a appropriate half reaction. You dig it out on this sheet, okay? But you really didn't have to either, because you could have, you didn't really have to. It might be more difficult doing it this way, but if the half reaction using these two, there's only one way to do it. Ag plus an electron makes Ag solid. Okay, so that would work too. Okay, but either way you want to do it. Oh, we have to do what first before we can use our mole bridge? The technical word? Yeah, you're right, but molar mass. We need the molar mass of silver. All right? Grams of silver in a mole of silver. And then we'll have our moles of silver per moles of electrons. And then we'll have our answer. So we need the molar mass of silver. Matt, you see it?
Yeah.
107.9 or something. In 1 mole of silver. We need our mole bridge. Vanessa, what can we say our mole bridge is going to be? Moles of electrons to moles of silver. The ratio would be, yeah, so what numbers are we going to put there? Yeah, just 1 and 1. Right? In this case, they're 1 to 1. They're not always going to be 1 to 1, but it's 1 to 1. Okay. So, 45 divided by 107.9, about 0.417. So that's the number I have to put in right there. And I'll get my joules. So 0.417 around what, 46,275? Somewhere around there, depending on your rounding. Now, do you see where I kind of messed up a little bit? I forgot the negative. Now, what does the negative do in there again? It's not that it means the little battery or the system, the cells, they lost energy, right? They did work. So that's why the minus sign is there. Okay. Now, let me try to confuse you a little bit. That's my job. This is the wrong half reaction. You notice that? Because the 2's, really the half reaction is 2s, 2s, 2s. My mole ratio should be 2/2. Did it matter? No. Didn't matter. Look at 1-to-1. So you don't need, that's why it's kind of key and appropriate half reaction. Just any half reaction that fits, right? That involves what you're interested in to moles of electrons. The ratio will be the same. It doesn't have to be the exact one. Okay. And that's kind of a hint to what's coming up. But standard cell voltages. If a cell is made with all concentrations 1 molar, right? So you make these batteries or these cells, electrochemical cells, make the concentrations 1 molar. Any gas, make sure its pressure is 1 atmosphere. Make sure the temperature is controlled at 25. Then you're going to measure what they call standard cell potential. Now, they do that because guys in Europe, guys in Taiwan, guys in Japan, guys in America, wherever, right? If you're going to make batteries or do anything electrochemical, you want to agree, you need something to measure things from. So if you're in Taiwan and you make this cell, or you're in Japan and make this cell, or America make that cell, you're going to measure the exact same voltages as everybody else. So if everyone's going to get the exact same voltages, why not just tabulate them? That's what they did. Right? That's what's in the handout. All reactions get all tabulated. Now, if you look at these half reactions, I don't know if you've noticed this, but all the electrons are on the what side? Yeah, the left side. They're all reactants or products? They're all reactants. Did you notice what's happening to the oxidation of the products every single time? They're getting reduced or oxidized. They're getting reduced every single time. So they call these reduction potentials. So you can kind of think of it as, oh yeah, the oxidation states are going down. Or the electrons are always on the reactant side. So that's how these are tabulated. Okay. So what you can do, we've already taken cells and divvied them up into 2 half reactions. Well, what would you measure if you hooked up the voltmeter to it? Well, you just add up the half reactions. The cell. Now, let's back up a little bit. What makes this standard? It has a little circle there, right? You see those little superscript zeros? That means standard. So this is how you get standard cell potential. So you can just add up these halves from these tables, and that's what you're going to measure on the voltmeter if everything's under standard conditions. That's the only time this is going to work. Okay? So the only trick to doing this is just to make sure that, because one reaction is going to be reduction, reaction is going to be oxidation. So that's going to be a flipped reaction. So you have to flip it to see it. And if you flip the reaction, what do you do to the number you read? You just change the sign. Okay? So let's try a couple of these. So let's pretend these are our half reactions. Pretend this is a half reaction, A, B, and C. Each of these are individual half reactions. What number would you end up plugging into this equation is all I'm really playing with. Okay? So we have the first one. Nickel plus 2 electrons gives nickel solid. Okay? Nick, what voltage, what standard cell potential correlates with that half reaction? He says negative 0.23 volts. Now to back up a little bit, when he was looking for it, when you look at this reaction, it's written as a reduction, or you can see it as electrons on the reactant side. So that means that reaction is going to be in here verbatim, right? So you just you don't have to be flipping any reactions or anything. He just read it as negative 0.23 volts. Now let's say the half reaction is B. Notice the electrons are now on the product side. So if you want to go searching for it, you have to go searching for a reaction that's flipped, right? See, it's this one, it's A. What's going to be the cell potential for B, Pablo? 0.23 volts, positive. So you can do it 2 ways. You could, use a table, which is what you're going to have to do. But when A, you got to flip it. Okay. This is where it gets confusing, I think, Jessica. Vaughn. C. Right? They flipped it, and they also multiplied through by 3. Now, right? That's a very typical half reaction for a cell. You can see writing this. Remember, you got to cancel the electrons and stuff. You're going to be multiplying through by 3s and 2s and whatever. So what cell potential do you plug in for this? What would you guess, Victoria? Wait, 23 volts. And then, wait. Well, the positive 0.23 volts, and then do what maybe to it? Multiply it by 3? That's the question. Does everybody agree with this part, though? Yes. The positive 0.23 volts. That makes sense. This part doesn't. The answer is 0.23 volts. Let me tell you why. These guys, why is this thing so damn big? You have a D cell, A cell, AAA. This guy is so big because there's more what in here? More. What gives you the electron? The reactants. Right? I don't know. Somewhere I told you the reaction inside this battery. Go back a few, and they're ugly. They've used the cheapest compounds they could, and there's base in there. That's why they're alkaline. But just jam more reactants in here. It's not going to change the 1.5 volts, but you have more reactants. Now this thing is going to last longer, right? So you can put these in those little cars that go. They don't put in the little AAA. They put in the D's, right? So the dang thing is going to last longer. You're going to be changing those the skinny ones are the AAAs, right? You'll be changing those out all the time if you ran your big cars on that. Okay? What's that? Yeah. Or you could use a bunch more of them, right? Okay. So you mess with the amount, it doesn't change the potential. It doesn't make the hill any higher. Okay? It's just the same. You have more stuff is also it'll last longer. So that's the thing to remember with this, is all you do is with a half reaction, if you flipped it from the table, change the sign. You don't care about multiplying through by numbers. That doesn't change anything. Okay. So let's try this first question here. Let's find the overall cell reaction and the standard EMF. Okay, Lewis, how do we find overall cell reaction if we're given that nice cell notation there? Yeah. So how are we going to get it? Yeah. We're going to add up the what to get it? The what reaction? Add up the half reaction, right? So we're going to be adding up one half reaction. Add up the other half reaction. And then we'll get the overall. Just make sure what cancels? The electron. Okay, now remember this. These guys, that is a reactant or product? Reactant? Yeah, right? So we'll just throw them in there. Reactant. Product. Reactant. Product. Okay. From Ariella, how do you balance that top one? Yeah. Now you could go and look it up in the standard reduction potential table, but it's a lot easier just to, right? Make sure the charge is the same on both sides. And the bottom one, Alexa, how do you balance that half reaction? Yeah. Okay, now if you add these up, Destiny, will the electrons cancel? No, so what should we do? Yeah, multiply by 2. technically the bottom one times 1, but... Oh! Jeez, yeah. 2, 1, thank you. Okay, so that means we're going to have a nickel and 2 silver ions. And a nickel ion and 2 moles of silver solid. Okay. That way our electrons cancel. Now we need to write... Let's find the E0 for each of those. Jessica, Roja. What's the E0? Oh, did we find the E0 for that top one? That looks familiar. Is it positive or negative 0.23? All right. For this half reaction, nickel solid goes to nickel plus 2 electrons. It's the positive 0.23. Right. So we could look it up in the tables, but we already did once. We have to look up the bottom one in the table, though, Javier. That 1 electron plus a silver ion goes to silver solid. That one we have to look up. Positive 80? Okay. Now, do we care if it's multiplied through by 2? Nope. So add them up, you get 1.03 volts. There's our standard EMF. There's our E0 cell. And here's our overall cell reaction. Okay. Any questions on that one? Here's the whole kit and caboodle. All right? This is it. Everything's in this question. Find the maximum work that can be obtained from 28 grams of tin in the below cell if the EMF is 0.55 volts. So just imagine 28 grams of tin in that little Energizer battery. That's all there is. All right? And I doubt if it's going to stay at 0.55 volts, but you just got to pretend the whole time that tin's reacting. Okay, how much work can you get done? Mallory, you have a game plan for us? Okay, she's talking about, right? She's right. You could also answer the question, oh, let's find the overall cell reaction, or let's find an appropriate half reaction. And those are all right, but there's a better answer. Use the W max. The reason why I'm harping on this is general chemistry. This is one problem out of a bunch of different problems, right? Seemingly unrelated, but they are related. If you start with what they're asking for, there's logic to it. It guides you where you should go. There's no extra work. You approach the exact same problem the exact same way every single time. No memorizing. It's just logic. So they ask for maximum work. We have an equation for it. Slap it down. That's my strong suggestion. Okay. Now, Mallory said, okay, we need the number of moles of electrons. That's what she was after, right? You need to find F. You need to find E cell. See if you can figure this out. I'll be glad to help you. You need an appropriate half reaction to get the mole bridge. Okay. If you're not sure, just ask. Where to start? You see where to start? You can find what F is. F is in here, right? You need to find E cell. Remember, that's in the question. So you already have 2/3 done. Then you've got to find the N. right? And in the end, you got to convert the 28 grams of tin all the way to moles of electrons.
In order to find what's the ratio, I need this right now?
Yeah, you need an appropriate half reaction. So you know 10 and 10 plus 2, write a half reaction between those two, or look it up.
Yeah, no, it needs too much SN as, yeah, 2SN plus 2 plus 2.
There it is. There it is.
To be 2 to 1, or to be 2?
Yeah, write it out. You'll see it. It'll work. You got it. You're on the right track. No, in fact, this way it won't help you because you have your tin solid, but you don't have electrons in there. This reaction works. There's this one to that one because that's the ratio you need. What's 10 power? 118.7. Thank you, sir. So when you're messing with this, how did you figure out the ratio, right? Mole of tin to moles of electrons. Yeah, you need an appropriate half reaction, right? A reaction that involves tin and electrons. So you can go out and figure out the whole overall reaction, but that's not going to help you because you don't have a bridge between tin and electrons. The electrons canceled out. You went too far. What half reaction do we have to write? Okay. Now let me stop you right here, though. Sn going to Sn plus 2. Yeah, just use this. Coming right from there. And Sn going to Sn plus 2. And then plus how many electrons? And they have to be on which side? Yeah. So there's your whole bridge. Has 2 of these guys for every one of those. Okay. So now we can finally get W max. Where did you get the E cell? 0.55 from the problem. You don't get it from the table, right? Because there's no superscript 0 on there. It's something that has to be measured. Right? It's not standard. So you measure it. E cells is measured. Somewhere around 25,000 or so. Well, negative 20 joules, negative 25 kilojoules, somewhere around there. Okay, depending on your rounding. Any questions on that one? Those are the tough questions. Something like this, then we'll call it a day and hand back the exam. Find the overall cell reaction and the standard EMF for this cell. Oh, it should be joules. It should be energy, joules. Now, one person got 0.33 volts. Did anybody else get that? That's what you should be getting. If you got it, you're doing it right. How many electrons canceled when you got that? 6? Okay, so if you're getting 6 electrons to cancel, and .33 volts, you're doing it right. Any questions on it? Now, don't let the exam get you down over the weekend. You didn't do as well as you did in the past as a class, but we have an exam retake. We've got exam 4. And this exam 4 should be a real grade booster, I think, right? The majority of your exam points coming up in this class. So, our high scorer was Mariella. Congratulations. You buy a beaker from her.